Okay, welcome to Robotics 1, and we are discussing Chapter 8, which is Motion Control System. In the last class, we talked about what do we mean by eigenvalues, and then we looked at how to convert a second order equation into a first order equation. And that information is super important because in today's class, we will try to solve problems using MATLAB with that technique. Now, I just want to clarify that there are multiple ways. So there are multiple ways to solve a differential equation. And in your differential equations class, you must have been introduced to different techniques on how to solve the differential equation. One useful technique is something called as Laplace transform. And in today's class, I'm going to talk about how to solve using Laplace transform. And then we would use MATLAB to solve differential equations using Laplace transform. Now, first and foremost, let me give you some intuitive explanation. So, and this explanation is not mathematically rigorous, but it kind of makes sense. First and foremost, why do we need Laplace transform? And what is the need for Laplace transform? And I'm going to start with a very simple example, something called as logarithms. And I believe most of you have studied logarithms in high school. What is the biggest advantage of logarithms? So what I want to do is, I want to give you a number. So something like, so I have this huge number that needs to multiply with another huge number. So, and then I want to find out the multiplication of these two numbers. Now, please try to understand, if you have MATLAB or if you have calculator, this multiplication probably is easier. But think about if these numbers have 15 or 20 digits, and then if you want to perform multiplication, it may take some time, but with calculators and computers, this multiplication can be performed. Now imagine yourself in 1960s or 1950s. So at that time, the computational power that we have available now was not available. So what they did, the scientists and engineers used a technique which is called as logarithms. What does this logarithm do? I will not go into the definition of logarithms, but what it means is when you take the log, this large number gets converted into a small number, and I'm just guessing here, say 2 point or 23.27. So this log number is a very small number. Once you take the log of this number, and multiplication gets converted into addition. So this becomes like 46.23, and I'm guessing. So I don't know if these are the actual log values. So the idea is this multiplication operation, which is very time consuming and tedious, got converted to an addition operation. And this addition is performed with small numbers. So this addition, and again, I'm guessing, maybe it is something like 78.32. this addition is easier to perform. And when you take the inverse log of this number, you would land up with a very large number, which is nothing but, so I'm going to call this answer here, is equal to answer. So what has happened here is by logarithm, you used a transform to convert a very complicated and very long multiplication operation into a simple addition. So let's look at the steps. So initially, you had this system. So this is this multiplication operation. You took the log of it. Once you took the log of it, then this, so I'm going to call this A and B. This got converted to a simple operation, that is addition, and these numbers are small. And then you take antilog of the value of C. So you got this. So with logarithm or with log transform, the multiplication operation got converted into an addition operation, and then you did the anti-log and you got the initial answer. So Laplace transform exactly does the same thing. So if you have a differential equation, and I'm going to write this differential equation something like this. So this is the differential equation. And now you're going to take a Laplace transform. So once you take this Laplace transform, this differential equation gets converted into an algebraic equation. So differential equation gets converted to algebraic equation. What do I mean by algebraic equation? So please try to understand the equation that I have written does not include or does not have any derivatives. So please note, no derivatives here. Derivatives exist here, but there is no derivative here. So you can solve this algebraic equation. So you will solve this algebraic equation, and then you will do inverse Laplace, just like anti-log or inverse log, and you will get your solution x of t. This is the fundamental advantage of Laplace transform. Just like logarithms, logarithms are used to simplify multiplication operation. A multiplication operation gets converted to a simple addition operation. Laplace transform takes a differential equation and converts that into an algebraic equation. Algebraic equation means the equation that is just plus minus, no dots, no derivatives, no with respect to time, no integration needed. So basically you get this algebraic equation and the solution of the algebraic equation. You will find the solution of the algebraic equation. Once you take the inverse Laplace of that solution, you will get the answer in the time domain. So this is the fundamental principle behind the Laplace transform. And Laplace transform is super useful, but there are certain limitations. A Laplace transform can only be used for linear differential equations with constant coefficients. Now let me answer this. What do I mean by constant coefficient? Last time we looked at the equation mx double dot plus cx dot plus kx is equal to 0. So this is the equation when on the right hand side it does not have any external forcing. Or maybe you have an equation mx double dot plus cx dot plus kx is equal to say f cosine omega t. So you have forced problem and you have the unforced problem. So this is unforced and this is forced. Laplace transform can solve equations like these very easily. But Laplace transform cannot solve equations. So imagine that now you have an equation mx double dot plus cx dot plus kx cube is equal to 0. So this term is actually a nonlinear term. So nonlinear term. So Laplace transform cannot solve equations with nonlinearity. The other terms, other type of equation Laplace transform cannot solve, it's something like this. Now you, in this particular case, you have a time varying mass and say you have a time varying stiffness. So this here mass and stiffness, these two terms change with time. Laplace transform cannot solve equations where the coefficients, so this is the coefficient that is changing with time. So if you have differential equations like these, you have to use different technique. So no Laplace transform. However, MATLAB with the numerical integration can solve equations like these. And if you recollect, the robot equations that we derived were nonlinear in nature. So what I'm going to do is I'm going to work out a few examples that we can solve manually with Laplace transform. And then I will show you how to use MATLAB to solve problem using Laplace transform and other techniques. So at this point, let me give you the definition of Laplace transform. Laplace transform of f of t is given as integration of 0 to infinity e to the minus st f of t dt. So f of t dt. Probably you have seen this equation written in slightly different form. That means the same thing, f of t e to the minus st dt. Now I want to be careful here. S when is the Laplace transform variable. Transform variable. And t is the time. In last class, I talked about time domain and frequency domain. In that case, frequency domain always utilizes Laplace transform. So this is a very important note. To solve systems or to analyze systems in frequency domain, we use Laplace transforms. Now, how do we find out the Laplace transforms? And S, and this is something similar to what we talked about the eigenvalues. S is actually a complex number, and where this is the real part of the complex number and this is the imaginary part of the complex number. So Laplace transform technique is super duper important, And when we are going to study systems in frequency domain, Laplace transform will be used everywhere. Now, I'm going to take few problems just to give you an idea of how to find Laplace transform. Typically, if the problem is simple, only then we use hand calculations to find Laplace transform. Otherwise, most of the times we are going to use MATLAB to solve Laplace transform problems. But once again, Laplace transform is super important, that is used to convert differential equations into algebraic equations. So if somebody asks you, hey, what is Laplace transform? You should tell that person without hesitation that Laplace transform takes a differential equation, which is something like x double dot, and converts that into an algebraic equation, which is something like s square. Any questions at this point? This lecture is super duper important because later we are going to use the Laplace transform tools to analyze the systems in the frequency domain. So I plan on going very slow when I discuss Laplace transform, its application. But if you don't understand, please raise your hand and I will unmute you and answer the questions before I proceed further. Okay, so let's find out the Laplace transform. Now, let me talk about some important functions. So the first function is something called as step function. What is a step function? Step function means, think about it like it's just like a step. So you have, this is time, and initially uh, the value was 0, and all of a sudden value became a constant a. So if you look at the way the step function worked, when the time was less than 0, this is when the time was less than 0, you can think of like before the Big Bang, the magnitude was 0, and just at the Big Bang, magnitude became a, or a constant. And this function, I'm going to write this as f of t because time t is on x-axis, is written as 0 for time t is less than 0, and f is equal to a for time greater than equal to 0. Or for greater than 0, the function became a constant value. And you can think about it like you're climbing a step, you're climbing a step. This is just like a step function, but we are using one step. And now what I want to do is I want to find out the Laplace transform of this step function. What is the equation for the Laplace transform? Laplace transform of f of t is given as integral 0 to infinity f of t e to the minus st d of t. Now I'm going to perform this integration, and I want you to be careful and observe the way I'm doing. One thing I want you to note, the variable that I'm integrating with respect to is dt, and that variable is here. So when I'm performing this integration, s would be treated as constant. So check this out. So Laplace transform is something like 0 to infinity, 0. Then, so I need to write this function down here. So I need to write this function down here. This function is 0 when time t is less than 0. So it doesn't appear because our domain is from 0 to infinity. This function f of t becomes a e to the minus st dt. And when I try to find out e to the minus st, the derivative, the integration of this function is going to be a e to the minus st divided by minus s. And this is 0 and this is infinity. Now what I need to do is, please note, these are the values of t. So t is equal to 0 and t is equal to infinity. So what I need to do is, I will have a minus s e to the minus s infinity minus e to the minus s 0. And as you can see, once I solve this, I get minus 1 here. This is 0. And I get a divided by s. So Laplace transform of step function is a divided by s. So in the time domain, and in Laplace domain, if I have a step function 0a, then in the Laplace domain, this is going to be a divided by s. Now let me take one more example. Just for the completion purposes, we many a times we use unit step function. So unit step, that simply means the value of a is equal to 1. So when the unit step function is used for analysis, it just means a is equal to 1 and the Laplace transform is just 1 divided by s. Next function I want to talk about is something called as the ramp function. Now, ramp function is something similar to the ramp. In other words, it's something like this. And step function, ramp function, impulse function, all these are important functions because they can be used to understand the system behavior. Now let's see, how does this ramp function look like? So ramp function, if you think about it, it's like a straight line. So this is f of t over here and this is t over here. So ramp function is given as f of t is equal to 0 when t is less than 0 and f of t is equal to a times t, where a is the slope. So a is the slope. At when t is greater than equal to 0. So now I need to find out the Laplace transform of ramp function. Again, the equation for Laplace transform is Laplace transform of f of t is equal to 0 to infinity f of t e to the minus st dt. And what I'm going to do is, I'm going to use this equation. Initially, at when time is less than 0, the function is 0. So when I perform this integration, 0 to infinity, this becomes a of t e to the minus st dt. And now what we need to do is, we need to perform the integration. So please note, a is a constant, so that can go out. But now I have two variables. I have t and e to the power st. And believe it or not, we have to use integration by parts. And when we use integration by parts, I hope you remember the equation for integration by parts. This equation becomes at minus s e to the power minus st evaluated at 0 and infinity minus 0 to infinity a e to the minus st divided by minus s dt. And perhaps some of you have forgotten integration by parts rule. So integral u dv is equal to uv minus integral e du. So, and then which term to use first and which term to use second, there are rules, and there are, we can actually get this integral using MATLAB as well. So if there is time, I can show you that we can, how we can get the answer. But at the end of the day, once you solve this, this is going to become a divided by s square. So Laplace transform of a ramp function is a, which is the slope of the ramp, divided by s square. Any questions here? So this is integration by parts. Next, I want to work out is a sinusoidal function, a sine function. And say, let's consider this sine function is given as f of t is equal to 0 a sine omega t. So when time t is less than 0, the function is 0. When time t is greater than equal to 0, that function is a sine omega t. Now, what we want to do is we want to solve this using Laplace transform. But before I solve it with Laplace transform, let me remind you of the identity that I kind of discussed or mentioned in last class. E to the j omega t, where j is square root of -1, is nothing but cosine omega t plus j sine omega t. And the next term is e the minus j omega t is equal to cosine omega t minus j sine omega t. And what I want to do is, from these equations, equation 1 and equation 2, I would like to find out value of omega t. And you can clearly see, if I subtract equation 2 from equation 1, cosine omega t gets cancelled, and I land up with an expression for sine omega t. So sine omega t is given as 1 divided by 2j e to the j omega t. This comes when I do 1 minus 2 e to the j omega t minus e to the minus j omega t. So this is the representation of the sine function in terms of exponent. So now when I do the Laplace transform of f of t is equal to, again, integral 0 to infinity f of t e to the minus st dt. So what I'm going to do is 0 to infinity, and this is a, so I'm going to multiply by a here, a here. This becomes a divided by 2j e to j omega t minus e to the minus j omega t multiplied by e to the minus st dt. Now This becomes super simple because a divided by 2j comes out of the integral sign, infinity, e to the minus st gets added, so you get e j omega minus s t minus e minus j omega plus s t dt. And then you can perform the integration, and when you do the integration, I'm just gonna give you the answer. It's similar to the first problem where you get the integration result like this. This equation becomes a omega divided by s square plus omega square. So this is the Laplace transform of the sine function. Now, if you have a lot of time, you can very well find the Laplace transforms of many functions. But for practical purposes, what we have is we have something called as Laplace transform tables. And I would just like to draw some analogy. So in the Laplace transform tables, you have functions in the time domain, and you have their representations in the Laplace domain or S domain. So this is called as time domain, and this is called as Laplace or S domain. And this is exactly similar to the number and the log of number. So if you look at the logarithm tables, s square plus omega square. Okay. So Laplace transform tables are something similar to log tables. Log tables, wherein what you have is you have the numbers on the left hand side and their natural logs on the right hand side. You also have inverse log tables, wherein you have the log on the left hand side and the numbers on the right hand side. So you can actually go from right to left, or you can go from left to right. We are going to do the exact same thing. So given the function in time domain, we can find the function in the Laplace domain. Given the function in Laplace domain, we can go back and find the function in the time domain. And again, we are not going to derive these, but I'll just tell you unit impulse is 1, step is a divided by s, ramp is a divided by s square, e raised to plus minus at is given as 1 divided by s minus plus a, sine omega t is given as omega divided by s square plus omega square, cosine omega t is given as s divided by s square plus omega square, and so on. So if you look at the Laplace transform tables, you will see tons and tons of Laplace transform tables. So there are lots and lots of functions. But here is the most important part. And this is something that I want you to remember. Most important part. If you have a derivative, d by dt, its Laplace transform is s. What I mean by that is let's start with something like this. I'm going to have a time domain representation, and I'm going to have a Laplace domain representation. In time domain, my independent variable is time. In Laplace domain, my independent variable is s. If I have a derivative, let's just say, let's start with the function. I have this function x of t, and I have to be careful here not to create any confusion. I'm going to call this small x of t. In Laplace domain, I have capital X of t. If I take the derivative in the time domain, this becomes x dot t. In Laplace domain, when I take the derivative, it becomes s x of s. If I take the second derivative, x double dot, in time domain, this becomes s square x of s. So what I want to say is this. This is the most important thing that you should remember. In time domain, differentiation is represented by d by dt. That becomes multiplication by s in the Laplace domain. What happens with the integration? Integration in time domain is nothing but integration of one uh, integral of dt. It is inverse of the differentiation, so it becomes 1 over s in Laplace domain. So these two are super important relationships that we use a lot when we try to solve problems using Laplace domain. So I'm gonna, this is so important that I'm gonna repeat this once again. It doesn't matter if you don't remember these Laplace tables. So the tables that I have over here, even if you don't remember, that is okay. MATLAB will help you with that. But the most important part that I want you to remember is in time domain, your independent variable. So independent variable is time. In Laplace domain, your independent variable is s. Your dependent variable in time domain is say small x comma t. In the Laplace domain, your dependent variable is capital X comma s. In time domain, if you are taking the derivative, so if you are taking the derivative, the Laplace domain, it becomes a multiplication, and that is super important. There are no dots in Laplace domain. There are just multiplication by s. If you take a double derivative, then it becomes s square. Essentially, the equation gets multiplied by s x of s. So you land up with s square. And this is the super duper important part that you should remember. Whenever you are performing the derivative, d by dt, you have s. If you perform integration, you will have multiplication by 1 over s. Before I proceed any further, I just want to ask you if there are any questions at this point. So what I'm going to do is, however many derivatives, yes, that many times will multiply s. So let me give you some examples. And I'm not going to solve these, but just these are the examples. First example is, if you have a differential equation, something like mx double dot plus cx dot plus kx is equal to 0. This differential equation is in time domain. And now I want to convert this differential equation into Laplace domain. It becomes, it's very simple. Check this out. This becomes s square x of s plus C S x of s plus k x of s is equal to 0. So I want you to note x became this, x dot became cx, and x double dot became s square x of s. Let me take one more example. My example here is like x triple dot is equal to sine omega t. This is a differential equation, except I have three derivatives. This equation will get converted to something like s cube x of s is equal to, and we just looked at the Laplace transform of sine, and this is s square plus omega square. So now you have a differential equation in time domain, and I want you to remember what has happened. The differential equation means equation with the terms d by dt got converted into an algebraic equation. Now this equation can be solved with algebraic manipulation. Now how would I solve this equation by algebraic manipulation? Here is the simple idea, and let me give you just the idea. I'm not going to solve this, but here is the idea. I will find out x of s is equal to 1 divided by s square plus omega square, and this is my solution in the Laplace domain. So this is the solution in Laplace domain. This is the solution in Laplace. Now what I'm going to do is I'm going to use the inverse Laplace transform. I'm going to use the inverse Laplace transform. Omega is in top. Yeah, omega. Yeah, there is an omega on top, right? That's correct. So here becomes omega. So inverse Laplace transform, and either I can find the inverse Laplace transform directly, or I can use partial fractions or some other technique, or I can just look up tables. I will look up tables and find out x of t, and that will give me the answer in the time domain. Now, probably some of you have studied Laplace transform in calculus or differential equations class. But what I'm going to do is I'm going to use MATLAB to solve Laplace transform. So before I proceed and go to MATLAB, I just want to ask you if there are, Alexander, I am going to unmute you. You should be unmuted.
I noticed in the table that on the time domain there was e to the plus or minus at, and then Laplace there was s, then minus or plus. Does that mean that the Laplace has the inverse operation of the time domain, or is that a mistake?
So I kind of took a shortcut. So if you have e to the plus at in Laplace domain, it becomes s to the minus a. If you have e to the minus at in Laplace domain, it becomes s plus a.
I see. Thank you.
Okay. Any other questions before I proceed further? Now, what I'm going to do is, let me set up the problem. So what I want to do is, I want to solve this differential equation. I want to solve this differential equation using Laplace transform. So we are going to solve this differential equation using Laplace transform, but I am going to use MATLAB. So what I'm going to do is I'm going to go to MATLAB, but I want you to understand when I try to solve this equation in Laplace using Laplace transform, I need to convert the equation as a Laplace transform equation. So let me write this down. So this equation becomes m s x of s plus c s x of s plus k x of s is equal to 0. Now please note, everywhere in this entire equation, x of s, x of s, x of s is common. So this equation simply becomes m s square plus c s plus k x of s is equal to 0. So when we are going to solve this expression in Laplace transform, we will be programming it using the Laplace transform equation. And what I'm going to do is I'm also going to find out the analytical solution using MATLAB. So what we will do is we will use analytical or direct solution using MATLAB and then try to work out the problem. And just for completion, if you recollect in the last class, I told you how to write a second order equation into a set of first order equation. So if you recollect, in the last class, we said x d by dt x dot, and please note this is all done in last class, minus k by m minus c by m x dot. So we wrote the equation in this form. MATLAB requires equation in this form to be solved using numerically. So what I'm going to do is I will show you how to solve the same differential equation. And please recognize the differential equation that we are going to solve is mx double dot cx dot plus kx is equal to 0. And I'm going to give you some values. So say mass is equal to 0.8 kilograms, value of C, which is the damping coefficient, which is 3 Newton second per meter, and then K is the value of the spring constant, which is Newton per meter. Because when we try to solve the equations numerically, we need to have some values. We can't just go ahead and solve the equation symbolically, even though it may be possible for some simple cases. So I'm going to take this equation, which is a simple spring mass damper system, this equation, and then we'll try to solve this differential equation using 3 different techniques, M, K, and C. We'll try to solve this differential equation using 3 different techniques. One is analytically, which is just writing the equations and trying to find the solution. Second is using Laplace transform. And third is using numerically. So now this would be a good time to open MATLAB and then work with me as I go through this solution. So now you should be seeing my MATLAB command prompt. Let me make sure that, okay, everyone can see my MATLAB command prompt. So first thing what I want to do is I want to solve analytically. So the differential equation that we are going to solve is mx double dot plus cx dot plus kx is equal to 0. And to solve equation analytically, I'm going to use the value of m is equal to 0.8. I'm going to use value of c is equal to 3. And I'm going to use the value of k as 8. So for that, I have to use the command dsolve. This MATLAB command dsolve is to solve differential equations. Now this command goes something like this, and I'm going to type this in the chat window, and I will explain what this command is. So 0.8 d2x is the second derivative, which is mx double dot t. C is 3 multiplied by dx, which is the derivative of x, plus 8 multiplied by x is equal to 0, which is the right hand side of this equation. Everyone understood this? Now what is over here? Please understand, this is the second order differential equation. What do I mean by second order differential equation? That means it has two derivatives. So it needs to be integrated 2 times. When we integrate once, we need one initial condition. When we integrate 2 times, we need 2 initial conditions. So the first initial condition is on the displacement. X of 0, which is the initial displacement, is 1. Dx, which is nothing but the initial velocity, is 0.5. So this is the initial displacement. This is the initial velocity. Now what I want to do is I want to create a figure and I want to plot the solution. Now this equation will be evaluated symbolically. So I'm just going to create one figure, say figure 1, and I'm going to say the solution, and then I'm going to give you the time span 0 to 3, and then I'm going to give the range for the y values. And at this point, I want you to run this code, and when you run this code, it will give you a plot. And I'm going to change my screen to show you the plot. Are you able to see the plot? This is the plot you should be getting. Any questions here? And if you look at on the top, you have the expression that talks about the solution. So this is how the solution should look like. Now what I'm going to do is I'm going to make few changes. I'm going to go back to the same MATLAB code. Now you should be seeing my MATLAB code, and I'm going to make the value of damping 0. So I'm going to make value of damping is 0. So please note I changed the value to 0. Now since there is no damping, I should be seeing oscillatory response. Once again, run this code, change the value of damping to 0, run this code, and now I'm going to share my results, and you should be seeing a sinusoidal response. One thing I want you to notice that this is the response for the displacement. This is not the velocity response. This is just the response of the displacement. And that's why you're starting from 1, it's going to -1, going up from 1. So this tells me that this is the response for the displacement. Any questions at this point? Now I want to make one more change here, and I'm going to go back to the MATLAB screen. You should be seeing my MATLAB. If you see my MATLAB, there is one more change I'm going to do. Check this out. The right hand side of this equation is 0. What that tells me is there is no external forcing on this system. The right hand side of this system is 0. There is no external excitation on this system. So what I'm going to do is I'm going to change this. I'm going to change this to say sine t. Sine t. And I will again solve this expression. And now you would see, I want you to go, I'm going to show you my results, and you would see the results, something like this. Everyone is able to get the same results? Any questions? Now I'm going to change this back to what it was. So what I will do is I will go back to what it was. This was 3, and the right hand side was 0. Now what I'm going to do is I am going to solve this using Laplace transform. So I want to solve the exact same equation using Laplace transform. The first step is I need to create the variables. So I'm going to create 3 variables. First is my time variable, which is the independent variable in time domain. Then I'm going to create S variable, which is the independent variable in Laplace domain, and capital X, which is the dependent variable in the Laplace domain. So I have these 3 variables. S is the Laplace domain independent variable. T is the time domain independent variable, and X is the Laplace domain independent variable. Now, since the right hand side of this equation is 0, I'm going to say F is equal to 0. And I'm going to take the Laplace transform of F. And this is just for discussion purposes. So F is 0. I'm just taking the Laplace transform of 0. Next is I'm going to set up the velocity term. Velocity term is s multiplied by dx. So the velocity term is, I'm gonna paste it over here. And one thing I just want to tell you, this -1 is nothing but the initial condition on the displacement. So the initial condition on displacement appears over here. Then I need to find out the acceleration term. This comes over here. And I'm gonna type this in the chat window. One thing I want you to note that I have dx1, d1x, which is the velocity, and I'm multiplying this by the term s. And I have the initial condition on the velocity, which is 0.5, that is over here. Please note that these initial conditions are exactly same as the initial conditions that we have when we solve the equation using dsolve. Now what I'm going to do is I'm going to form the algebraic equation, and this algebraic equation becomes this expression, which is 0.8 d2x 3 times d1x 8 times capital X. Yeah, F, that is correct. Capital F is equal to 0. So if you want to say F is equal to 0, so this is the F in the time domain. That gives me this F in the frequency domain. And then the last term is here. Is solve. And I want you to understand solve is a function that is used to solve the algebraic expression. So essentially, I have an algebraic expression that I'm trying to solve. And you are welcome to just say help solve, and help solve will tell you the function, how this function is actually used to solve algebraic expressions. So whenever you have a solve, solve will give you a symbolic solution of the expression, and then that equation can be solved. The next part is SOL is the solution of this whole expression. I'm going to take the inverse Laplace transform of this solution. And the inverse Laplace transform, the command is I Laplace. I stands for inverse Laplace. Copy, paste. And then I'm gonna create a figure. And I just want to create a different figure so that we can compare the solutions. So I'm gonna say figure 2, because initially I had figure 1. Figure 2, I want to plot solution again from the same range. So I'm going to run this code, just the Laplace transform code. Highlight, right click, evaluate, and then I get the solution, and Whether you remember this or not, this is the exact same as the very first solution that we got. And you should be getting the same solution. And at this point, I want you to run the code and confirm that you have the exact same solution as I do. Everybody got the same solution using Laplace transform? Okay. Now what I'm going to do is I'm going to go back to the MATLAB screen and I'm going to make some changes. So I just want you to note that I added this capital F on the right hand side of equation 21. Please note there are two equal to signs, equal to equal to. So if you recollect, this is the equation. And now I'm going to make the same changes that I made earlier. I want to solve the analytical solution. In the analytical solution, I want to add sine t on the right hand side. So in line number 3, I have added sine t. Here, I'm going to add sine t. So line number 13, I have f sine t and I have capital F over here. Now what I want you to do is, I want you to highlight the whole thing and evaluate the code. And once you evaluate the code, I want you to note is you will have two figures. One figure is from the analytical solution, that would be figure 1. Second figure will be from numerical solution, the Laplace transform solution, and I'm going to show you my solutions. First, this is the figure 1. This is the analytical solution. I'm going to show you the figure 2, which is the Laplace transform solution. And they look the same. Are you with me so far? Now I'm going to make one more change and I'm going to go back to my MATLAB script. I'm going to make my damping 0. So value of C is 0. Value of C is 0. So please note the two locations where I made the change. So this is made 0 and this is made 0. Now what I'm going to do is I'm going to evaluate, and then I'm going to share the solution. This is my figure 1. This is the solution from the analytical equation, which shows me a sinusoidal response. That is how it should be. That is what is expected. And I want to show you the response that I got from the analytical solution. The Laplace transform solution. Can you see that both these responses are exactly the same? Are you getting the same answers? Okay. Now the next part of the discussion is super duper important. So please pay attention. Now, my question to you is this. Right now, the damping is 0. So the value of C is 0. Damping is 0. What would be the eigenvalues? If the damping is 0, what would be the eigenvalues? I'm looking at the chat window. And just let me just make everything 0. So I'm gonna make f zeros. So my question is this, and this is a very important question. Damping is 0. What would be the eigenvalues? Since the damping is 0, eigenvalues will have 0 real part. Eigenvalues would be purely imaginary. There is no positive real number since the damping is 0. Since the damping is 0, the eigenvalues will have 0 real part. They will be purely imaginary. And I want you to very quickly go to the notes from the last lesson. When the eigenvalues are purely imaginary, the response will be oscillatory. So system, if you run this, you will see that the system behavior is oscillatory. So your figure 1 and figure 2 both will show you sinusoidal behavior. Next thing what I want to add is, let me make this damping as positive damping, which is the case that we looked at. Change this to 3, change this to 3. In the analytical solution, change the value of damping coefficient to be 3. In the Laplace transform equation, change the damping coefficient to be 3, and then run this code. And you will notice that the system decays at time t is equal to 3 seconds. Please observe, at time t is equal to 3 seconds, the displacement has become 0, which means the response has decayed. So what would be the eigenvalues in this case? Eigenvalues in this case will be with negative real parts. So the eigenvalues will be negative real parts. The last part which I want to conclude with is, let me make this damping negative, which means instead of plus 3, now this is minus 3, and here it becomes again minus 3. And now what I'm going to do is, I'm going to run this code again. Now I want you to look at the solution. You will see that the solution grows unbounded. Probably the easy plot is restricted for the values of y from -1 to 1, 1.2, so it doesn't see. You can actually take that thing out. So make this small change. Just remove this, and run this code. And you would observe that the system response is becoming infinitely large, which means the system response is growing, which means right now, when you have negative damping, in that case, your response is growing because the eigenvalues have positive real parts. And with this, I'm gonna stop, and then I would be happy to answer any questions you may have.